Turning to slide 53, we're going to take a look at adding residual correlations over time for the latent class indicators. And this draws on the techniques described in the 2015 paper by Tiermer and I in structural equation modeling. So this is applicable to both LCA and LTA. And the idea is that each indicator is allowed to have a residual correlation across time, and by allowing that in LTA, you are in effect able to perhaps find a big minimum for a given number of classes that you would otherwise not find. So for regular LTA, no covariates, we have the run that we talked about before, where we have no residual correlations, and now we're going to add residual correlations, and we're going to have 50 parameters, and the log likelihood is increasing rather quite a lot, and so is BIC. BIC is considerably lower or better than without the residual correlations. 50 parameters come about because for each item you allow correlation for adjacent time points. So with 4 time points you have 3 adjacent correlations between adjacent time points, and 5 items is 3 times 5 is 15, which is exactly the difference between 50 and 35 parameters here. Now for RI-LTA with numerical integration, residual correlations are not yet available, but one can also argue that it's not needed. As you see, even without residual correlations, we have a considerably better BIC and considerably higher log likelihood. If you think about it, the RI-LTA also allows correlations between the residuals across time. For each item, it's actually lambda times lambda squared. If that is the correlation that goes via the random intercept factor. So those correlations, however, are held equal across all the 3 time points, across all the 3 adjacent time points, I should say. Whereas with the residual correlations that we used for regular LTA, those 3 are different. But with the interpretation of the random intercept factor as a constant trait, individual differences that are constant over time, we hold those 3 residual correlations equal across time. So in that sense, we don't really need residual covariances. That little difference between them being unequal versus equal is too small to bother with. Now, here's how you set it up in Mplus. It's still type equals mixture, but now we have the parameterization rescov. So you have the regular model, regression of the C on C, and then you add, for the first item, letter recognition is correlated between time point 1 and time point 2, and time point 2 and 3, and 3 and 4. So those are the 3 extra correlations or associations for item number 1, and then you do that for all 5 items, and that's it. So that's an easy way to check it out. This is also possible, of course, with continuous outcomes, where you just use no special parameterization, but just use the with statements. Another way to modify the model is to change away from the lag 1 modeling, which is the standard in LTA. So here we have a picture of 3 time points, and we can then entertain the notion that maybe we have lag 2 relationships going on here. That is, C1 influences C3 directly. And with the 4th time point, you would have C2 influencing C4 directly. This is easily done. All you have to do is say what's in the heading here, C3 on C1, And with our 4 time points, we would say C4 on C2 as well, which means that you can also have C4 on C1 and have a lag 3 included. And this may be what this model that we looked at before make it not fit the data as well as we want to. That is, perhaps we've left out important lag 2 and lag 3 modeling. So let's take a look at slide 55 where we test this out. So first you have regular LTA and then RI-LTA. So the lag 1 model that we talked about, that we used so far, is this, becoming familiar numbers now. With lag 2, we add a number of parameters for the C3 on C1 and C4 on C2. And we see that the log likelihood goes up considerably and the BIC goes down to some extent, to a large extent. And if you take a log likelihood ratio test, chi-square test of the difference, 2 times this difference, testing model 1 versus 2, the chi-square becomes 276 with 8 degrees of freedom, which is the difference here. So it's clearly significant, which meaning that you would choose model 2, the one that's bolded here. Model 2 with lag 2 is preferable. Here we don't show the investigation of lag 3, but lag 2 seems to be needed. For RI-LTA, the corresponding numbers are here. We get an improvement of the log likelihood with some to some extent, but to a lesser extent than for regular LTA. The difference, testing 3 versus 4, gets a chi-squared value of 20 with 8 degrees of freedom, which really isn't that bad of a fit for this overall large sample size. And in fact, if you look at BIC, it is preferable for the simpler lag 1 model, even though the chi-square test would tend to lead you to model 4. So I conclude that lag 2 modeling is needed for both regular LTA and RI-LTA, but there's a much stronger need for lag 2 with the regular LTA. So once again, including that random intercept factor allows a correlation more directly between the time points 3 and 1 and 4 and 2. And so the RI-LTA picks up some of that. Now you may ask them, what does the lag 2 effects, what do they look like? And that you get out of Tech 15. We're going to take a look at how we investigate that in a second. And then you may ask, does lag 2 modeling result in different decisions on the number of classes? So that's something for you to investigate if you are interested. And what about lag 3? Does that lead to a different decision on the number of classes? So here then is how you would express these lag 2 effects in probability terms, where you combine different results that you find in Tech 15. So what I'm going to show you, you have to compute yourself, say by Excel, but the building blocks are obtained in Tech 15. So let's think about the effect of C1 on C3. And we're going to think of that as marginalizing over C2, the intermediate latent class variable. Because Tech 15 gives you if the probability of C3 given C2 and C1, but now we want only the effect of C3 given C1, that direct effect. So the probability of C3 being in a certain class, conditional on C1 being in a certain class, is a sum of 3 sums of products. First we have probability C3 equals A, C1 equals B, for C2 equals 1, and then for C2 equals 2, and then for C2 equals 3, times the probability that C2 is equal to 1, 2, or 3, given the C1 B value that we want to consider. So we get this conditional effect out of Tech 15. C3 given both previous latent class variables, C1 and C2, and C2 given its predecessor. So this sum of products is what you have to evaluate outside of Mplus. But that would give you the direct effect, so to speak, the probability of C3 in a certain class given that C1 is in a certain class. Which could be interesting, you know, the starting point, how does it affect, say, C3 or C4 in another setting. Now note that in lag1 models, you know, we're talking about how to express lag2 effects, C1 to C3, but in lag1 models, this may also be of interest for the reason that probability of C3 equals a certain class, given that C1 is in a certain class and C2 is in a certain class, that does not depend on B, doesn't depend on C1 being B. Probability of C3 is only a function of C2 in a lag1 model. We don't care about what happened before C2. There's no direct effect from C2 to C3. But if we want to calculate the probability of C3 equals A and C1 equals B, like up here, in a lag1 model, it's not independent of B. That is, the starting point does affect the probability of C3 equals A, as we saw already in the introductory example in segment 2. That is, this kind of a table that I've shown up here could be useful for you to compute in lag1 models as well, because they answer the question, how does the starting point affect the ending point?